We first start by making an apparatus to which our hose will be attached. The water hose is attached to a wooden block by use of zip ties. A tape measure is then attached with the edge of the water hose at the 5-inch mark. Okay, start the water. In the first experiment, we used one 50-foot hose attached to a regular water faucet. We can see that the water's height reads 2'5" on the tape measure, giving us a height difference of 2 feet. In the second experiment, we used 200-foot hose, or 4 50-foot hoses, to test the effects of head loss with the increase of length. As expected, the water's height is much less than that of the 50-foot hose. The height is at 1 foot 4 inches off the tape measure reading, or a delta of 11 inches from the 5-inch reference mark.
Originally we wanted to do this experiment with nozzle velocity, but our results were a little too high. In this experiment we compared two different lengths of hose, and we used Bernoulli's equation, outlet velocity, and the difference in the velocity between a 50-foot hose and a 200 feet hose. The Bernoulli equation is just the equation for conservation of energy, and you can get the Bernoulli equation by integrating Euler's equation. And basic Bernoulli equation states that pressure plus density times gravity times height plus density times velocity squared over 2 is constant. In our case, we have a hose, and we can use these 2 points. So first point is at hose outlet, and second point is the highest part of water body. Pressure is 0. The pressure is atmospheric actually. Height at first point is 0 because that's what we're measuring from. It's just a reference point because the real height will just be height 2 minus height 1, also goes to 0. So our whole equation will be v1 squared over 2g is equal to h. So v1 squared is equal to 2gh, and when we take a square root of that, we get our velocity. In first experiment, our height of water rose to 2 feet. So it went from 5 inches, that was our reference point, to 2 feet and 5 inches. And when we had 200 feet hose, it went to 11 inches. So if we plug in the formula here, we have our gravity, 2 times gravity, which is 32.2, and we have 2 feet, we'll get 11.35 feet per second, which, if we want to use metric system, is 3.46 meters per second. Do the same exact thing, we get 7.68 feet per second, or 2.34 meter per second. We can compare our 50-foot and 200-foot hoses using energy equations. So we have pressure head, elevation head, velocity head, and at the end we have losses, which is important because these two are the same. These all are same, and we assume alpha is equal 1 equals constant. We can say that v1 squared over 2g equals v2 squared over 2g plus hl, and if we plug in v1 squared over 2g, we'll get 0.61. If we plug v2 squared over 2g, we get to 0.27 meters. So we're left with hl, which is 0.33 meters, which is exactly 13 inches, same as difference between 2 foot and 11 inches, and that's 13 inches. So we conclude that's our loss. If you can edit, then we can talk after. What should I say? We were thinking. I don't think I recorded. Same thing.